Hey guys, how are you? I hope everything's doing great. So last week we talked about vectorization of logistic regression and gradient descent, and we finally finished the vectorization, and we saw how vectorization enhances the coding for the computation power to be way faster, as we compared code that takes with for loops, how long it take, and without for loops with vectorization, it could be up to 500 times faster. And from last week, we also briefly mentioned something called broadcasting. And I did say that I'm going to be talking about it more deeply later on. And today we'll be talking about broadcasting into a more deeper level. And it is also another technique that we can use in Python to help us not only code the computation power could be faster, but it's also simpler for us to read and understand what's happening for even if we want to debug later on. So today will delve deeper into how broadcasting really works in Python. Okay. Okay. So let's explore broadcasting with an example. In this matrix that you see here, that I'm showing, is the number of calories from carbs, protein, fats, of 100 grams of four different food. So you can see we have apples, beef, eggs, and potatoes. Okay. And for here in this example, for every 100 grams of apples, it turns out to have 56 calories from carbs. Okay. And much less from protein, which is 1.2, and also 1.8 from fats. Okay. Whereas in contrast, 100 grams of beef has more of 104 calories from protein and 135 from fat. Okay. Now, let's say your goal is to calculate the percentage of calories for, that are coming from carbs, protein, and fats. Okay. And so if you look at this column, okay, over here, uh, we can add all these numbers together and you'd get for 100 grams of apples, you'd get 56 plus 1.2 plus 1.8 would be 59 calories. So that's the total calories from for the apples. Okay, and so the percentage of calories coming from carbs would simply be 56 over 59, which would be almost 94.9%. Okay, and so most of the calories that we can see here are coming from apples and from carbs, whereas in contrast, with the calories from beef, most of them are coming from protein and fats and so on. So the calculation that you want really is to sum each of the four columns. Okay, so apples, beef, eggs, and potatoes. Okay, and put it in a matrix to get the total number of calories of 100 grams of apples, beef, eggs, and potatoes, and so on. Okay, and then divide them through the matrix. Okay, sorry. So as you get the percentage of calories from carbs, protein, and fats for each of the four foods, the question becomes, how can we do this explicitly without a for loop? And can we do that? And the short answer is yes. But let's see how we can do that into a deeper level. So what I'm going to show you how you can define a matrix A, and it's going to be a 3 by 4 matrix. As we can see here, that you have three rows, which are the carbs, protein, and fat, and the four columns are we have the four foods, the four types of food, the apples, beef, and so on. Okay, and then with one line of Python code, we are going to sum down the columns. Okay, uh, we want to sum all of them to get the calories for each food. Okay, and then we can get the percentage out of these numbers. So after summing the calories for each type of food, all we need to do is divide this by some protein, carb, or fat, and then we'd get the percentage of that item. Okay, so 100 grams of these different types of food, uh, and then I'm going to do a second line of code where it will divide all of these four columns by their corresponding sum. Okay, so if you didn't understand me very clearly, hopefully it will be clear in a second when we look into a Python code. So let's go to the Python code. 1 second. Okay, let me make this bigger. So here we are in a Jupyter notebook, and I have already written this first piece of code to pre-populate the matrix A. And with the numbers that we have seen before in the slides, okay, I've just put them here into a matrix. So you can see that 56 calories are from carbs, 1.2 for protein, and 1.8 for fats. Okay, so we have defined this matrix A, and let's first compute this. So you can see that here's the matrix that we have. Okay, and first we are going to compute calories. We're going to call it cal. It's going to be equals to a dot sum axis is equals to 0, and which means it is gonna sum vertically. Okay, when we do axis is equals to 0, this means it's gonna sum vertically, and we'll talk more about it in a little bit. Okay, and then after that we need to print cal. Okay, but this should be a capital A for a different second. Okay, and as you can see here, we got 59 calories for the apple, 239 for the beef, 155 for the eggs, and 76 for the potatoes. Okay, and then we're going to copy the second line of code, which is the percentage. Okay, and to find the percentage, we're gonna just call percentage is equals to A over cal dot reshape. And we need to multiply this all by 100 since it's a percentage. And you can see here, as we did it in the previous code, that 94.9 is the estimate calories uh, sorry, that the percentage of calories are most as 94.9 coming from carbs, almost 2% coming from protein, and 3% coming from fat, and so on for the other types of food. Okay, 1 second. Okay. And so we have worked out a kind of how we can calculate apples and how we can calculate the code and the percentages all through the code, all through uh, broadcasting. Okay, so let's go back to the code for a second. Yeah, let me go back to our part. We have done this. Okay, 1 second. Okay. So just to repeat the two lines of code that we had, this is what we have written so far in the Jupyter Notebook. Okay, so we said here that cal is equals to a dot sum with the axis 0, and we said the percentage is 100 times a over cal dot reshape 1 by 4. Okay, and axis 0 means actually that you want Python to sum it vertically. Okay, so this is here where when we want to define axis 0, we want it to go by a vertical summation, not a horizontal summation. So that's how we want to define how the matrix wants to do the sum. Okay, and whereas the horizontal summation, if you wanted to do the sum horizontally, we'd need to define the axis equals to 1. Okay, so here is the 0 summation. Okay, if we put axis to 0, and this is the default. So if you don't actually define axis to 0, it would take it by itself as 0. But if you wanted to do a horizontal summation, then we just have to then define axis is equals to 1. And you'll be able to write axis is equals to 1 or sum horizontally instead of vertically. Okay, and then this command here, which is the cal a over cal dot reshape. Okay, this is an example of Python broadcasting that we did exactly. And where you can take a matrix A, so this is a 3 by 4 matrix, okay, and you divide it by a 1 by 4 matrix. And technically, after this line of code cal, okay, the variable cal is already 1 by 4 matrix. Okay, so technically, we didn't really need to do that because it was already a row vector. But sometimes to make sure everything is correct, we do that. Okay, so I know it is actually a little bit redundant, but to always make sure that our code is going as we want, we would rewrite it as the way. But if we don't put the car with the tree shape, it should still work fine. Okay, and so the reshape command is a constant type, so it's not going to really take much of your computational power. Okay, and it's a order one, it's a all one operation that is very, very cheap to call. So always be encouraged to use the reshape command to make sure that your matrices are in the right contact format that you want it to be. And now let's explain in a greater detail how this type of operation works. And we had a 3 by 4 matrix, and we divided it by a 1 by 4 matrix over there. Okay, so the question becomes, how can you divide a 3 by 4 matrix by a 1 by 4 matrix? Okay, how is this possible to do such computation? Okay, so here's the equation that we're gonna do, and we're gonna go through some examples of broadcasting and how it actually happens and what's the logic behind it in Python. Okay, so if you take a 4 by 1 matrix over here, 4 by 1 vector, okay, and add it to a constant number, okay, and for the sake of examples, we're gonna assume that this number is gonna be 100. Okay, and we want, okay, to auto expand this into a 4 by 1. Since it cannot take it as really 100, it needs to auto expand it. Okay, so it will be also a 4 by this real number will turn into a 4 by 1 vector. Okay, and so then you just add those numbers. Okay, and it turns out it's going to be plus 100 for all of the vectors. Okay, and here is the answer that you can see right over here. Okay, let me put my highlighter on. So yeah, 1 second. So yeah, this is the answer that you're gonna be having over here. Okay, and you're just adding 100 to every element, and in fact, we use this form of broadcasting where that the constant, okay, sorry, the constant, like last time, B was used in the was used broadcasting. So last week in our lecture, we did use WT plus B, and B was just a real number, it's a constant number. And when we multiplied it, okay, or we added together, okay, this is what basically happened. Okay, we added every number uh, to every set of element, but in fact it doesn't really happen that way. This is how the operation is happening under the hood. Okay, and this type of broadcasting works with both column and row vectors as well. And in fact, we are similar. We use a similar form for broadcasting earlier, with the constant that we're adding to a vector being a parameter b in logistic regression. Okay, so here's another example. Let's say you have a 2 by 3 matrix. We have 2 rows and 3 columns. Okay, and you want to add it to this 1 by n matrix. So the general case would be if you have a m by n matrix here, okay, you add it to a 1 by n matrix, and what Python really does is that it will copy the matrix m times. Okay, so instead of 1 by 3 that we have, because we have 3 columns, it will make a copy twice. Okay, it will make it until it's m by n. So since we only have 2 rows, it's gonna do it only twice. So it's basically you're gonna extend this, and it will make a copy of this, and it's gonna go downwards. Okay, and then it will become a 2 by 3 matrix plus a normal 2 by 3 matrix, and here is the sum right over here. Okay, so it will just multiply or make copies by the number of m if it's a row vector. Okay, and if it's a vector, it just makes so many columns until we reach the m by n matrix. Okay, so here you have to take your column and add it 100 in the first column. Okay, as you can see, all of the first column are added by 100, all of the second column are added by 200, and the third is added by 300. This should be 306 actually, not 606. So this should be 306. Let me fix it. Should be 306. So, okay. This is basically what we did in the previous slide, except that we use a division operation instead of an additional operation, but it doesn't really matter. Okay, so it doesn't really matter if you're adding, subtracting, multiplying, or even dividing. So let's give a final example here. Okay, and we have an m by n matrix. Okay, and you add it to this m by 1 matrix or a vector. Okay, so here is an m by n, and we have an m by 1 matrix. So again, similarly, this will just make a copy n times what we have. So since we have three more column, 2 more columns extra than this one, it's gonna make 2 extra copies. Okay, and it will make this copy horizontally, of course. So you will end up with an m by m matrix. Okay, and those 3 times, since n is 3 times the matrix n, so it will be looking something like this. Okay, it's gonna be copying this multiple times. Okay, And you add those together, and you'll have something that will be looking like that. Okay, so you'd see it's going to be 100. All of this row will be added by 100. Okay, and all of the second row will all be added by 200. Okay, and here is a more general principle of broadcasting. Okay, let me erase this. It's still stuck from the previous slide. Okay. So here's a more general principle of broadcasting in Python. So if you have an n by n matrix right over here, so yeah, so if you have an n by matrix right over here, and you want to add, subtract, multiply, or divide, okay, it doesn't really matter which operation that we're doing with a 1 by n matrix, then this will copy it n times into an n by n. So it's gonna keep doing it until it reaches the original first matrix, which is an n by n matrix. And then apply this addition, subtraction, multiplication, or division element, okay, to whatever. If conversely, you were again to take an n by n matrix right over here, okay, and you do the same operations, you add, multiply, subtract, or divide with an n by 1 matrix right over here, okay, then this will also allow us to copy it n times until we turn it into an n by n matrix. So it doesn't really matter if it's a 1 by n or an n by 1 matrix, as long as we all turn it to an n by n matrix. Okay, and it doesn't really also matter which element that we're using. So just one of the broadcasting, which is a n by 1 matrix. Okay, so that's just really a column vector. So it's like 1, 2, and 3. Okay, and so on. And you can add, subtract, multiply, or divide by any real number. And if you want, you can say it's a 1 by 1 matrix. Since it's a real number, it could be 5, 10, 100. It is only one number. So you can really assume it is a 1 by 1 matrix that has one row and one column. Okay, and for this example, we're going to take 100. Okay, and then you copy this number m times. So how many rows do we have it? We have to copy it by that amount of times. Okay, until you get another m by 1 matrix. Okay, so you'd see here, since it's a real number, we copy it 3 times. So it's going to be 100, 100, 100. And we're going to just add every row accordingly. So it will be 101, 102, 103. Okay. And something similar also works for row vectors. Okay. Here, you also have 100 as a real number. And instead of here we have a row vector, okay, which would be 100 just on every single column. Okay. Sorry, this should be this is actually, yeah. So it will be for every single column. And the fully general version of broadcasting, you can even do it a little bit more than this. And if you're interested, you can just check the documentation of the NumPy and look at broadcasting in that documentation. It will tell you more of a general definition of broadcasting and basically what we have covered so far. But what we have covered so far are really the main ones that you'll end up working with, okay, and using it when you want to implement neural network or logistic regression or whatever. So you're gonna get even a bit more detailed than this, but I would say that these are one of the most functions that you're gonna be using when you want to implement neural network, especially when you're feature engineering and creating new features. Okay, so that was broadcasting in Python, and I hope that you when you program, you come across these techniques and you fully understand what is going on in the code, and you know that we are doing this to make the code run faster, and also to help you run with fewer lines of code. So the purpose of this is not only to run the code faster, we're also running it with fewer lines of code. It will be easier to interpret, okay, and it would be obviously a lot better for the documentation. And now I still want to share some set of ideas that like are some tips and tricks that I have found to reduce the number of bugs in the code. So let's go to coding for a bit, and we'll see how do some. Sorry, 1 second. Okay, so let me delete this code. Okay. Okay. Anyways, the ability of Python will allow you to use broadcasting operations more generally, with a great flexibility of the Python NumPy program language. Okay, and it's more generally a great flexibility for the Python NumPy language, and it is also a bit of a strength and weakness for Python. I think Python is mainly a strength, okay, because it creates expressively the language and great flexibility, and you can do a lot of things with such fewer codes than other languages. Okay, but there is also a weakness because with broadcasting, uh, it is true that there is also flexibility with this code, but sometimes you can introduce very subtle codes or bugs that would look very strange looking bugs that you're not really familiar with the details of how broadcasting or how features look when broadcasting work. It might look very confusing if you're not really experienced with Python and how the logic goes behind Python. So for example, if you take a column vector and add it to a row vector, you'd expect it to throw up a dimension mismatch or a type error or something. But you might actually get back a matrix as a sum of a row vector or a column vector. And this is not always the case. Okay. And in normal mathematics, it shouldn't happen like that. But because sometimes Python works in a bit weirder ways, so we have to really be careful how we can write our code. Okay. And again, the Python have some logic that you cannot really do it in the mathematical world. Okay, but I would compute it in Python depending on the logic behind the libraries. And so there is an internal logic to these strange effects of Python. And if you're not familiar with Python, then it might get very confusing at times, and it's very hard if you want to find those bugs for you to debug them. So what I'm going to do right now is I'm going to share with you some couple of tips and tricks that are going to be very useful for you to simplify and eliminate all those strange looking bugs in your own code. And I hope with these tips and tricks, you would also be able to write code much easily that is bug free. Okay, with using Python and NumPy libraries. Okay, to illustrate one of these less intuitive effects of Python NumPy, especially how you contrast vectors in Python NumPy, let me do like something that is really quickly. Okay, so let's set, okay, A is equals to NP random of 5. Okay, so this creates 5 random Gaussian variables stored in an array, and so it lets A print five random numbers. Okay, So if you'd see here, you'd get some 5 random numbers. Okay. And when you want to print the shape of A, so you'd see that we have something that as a 5 comma. When you do this, when you do this kind of structure, you get something called a rank 1 array in Python. And it's neither a row vector nor a column vector. Okay, this leads to have some significantly non-intuitive effects. So for example, if I print A transpose, it ends up looking something similar to A. So let's check this out. A dot transpose, and it's going to be the same exact numbers. Okay, and they shouldn't actually look the same. Okay, and if I print the inner product between A and A transpose, so let's see here, print np dot. Oh, it showed it. Okay. You might think, okay, so here we got an answer. Okay, and you might think A times transpose A is maybe an outer product or it should give you a matrix. But if you do that, you get back a number. Okay, so what I'd recommend is that when you are doing a neural network, when you're coding a neural network, that you don't use data structure where the shape is 5 comma something. So when you see this, I don't recommend you to do that. Okay, and this the rank 1 array. Instead, if you want to set A to be this, so we should make it A is equals to np dot okay, a 5 by 1 matrix. And when you print A, you can see here, okay, it becomes a 5 by 1 column vector. Whereas previously, A and A transpose look the same. And now if you print A transpose, let's check it out right now, you'd see that it's different. Okay? Here that we have a 5 by 1 column array, and now this becomes a row vector. And this is how it should be actually. Okay, and now notice a subtle difference in the data structure, where 2 square brackets that you can see here, there's 2 square brackets, okay, and 2 square brackets here. Okay, previously there's 1 square bracket over here. So this shows that this is not really a 1 by 5 matrix previously. Okay, and that's the difference if you want to see if it is a rank 1 array or not. And if you print the dot product, the inner product, okay, so let's see, np print np we'd get actually, okay, a vector, and the outer product of a vector would give you a matrix. Okay, so let's look into, sorry. So look, this is the difference between doing some things that are literally similar to what we did, but just because we did not really put a comma, it did understand it as something else. Okay, so let's look at it in a great detail what we just saw here. So let's go back to the slides. Okay, so the first command that we ran was this one over here. A np.random.randn 5. Okay, and this creates a data structure with a.shape, which was a weird looking. Okay, it would look like something like that. Okay, and this is what we call it a rank 1 array. Okay. And this very weird looking data structure does not behave consistently as either a row vector or a column vector, which makes some of its effects non-intuitive and non-consistent. Okay, so what I'm going to do to recommend is that when you're programming or implementing logistic regression, okay, or neural network, that you do not use rank one arrays. Okay, do not use any of these arrays. Okay. Instead, every time you want to create an array, you commit to making it either a column vector, okay, like that. So it creates a 5 by 1 matrix, or commit it as a row vector. So it can be a 1 by 5 matrix. Then the behavior of your vectors may be easier to understand, first of all. Okay, since you can really understand this from the code that it's a 5 by 1 matrix instead of just 5. Okay. So in this case, a dot shape is going to be equal to 5 by 1 in this case. And this behaves a lot like a column vector. Okay. And in fact, it is a column vector. That's why that's why you can think of it as a 5 by 1 matrix where it is a column vector. And similarly, a dot shape is going to be a 1.5 over here. Okay. It's going to be 1.5 over here. And it behaves as here is a column vector, and here it's going to behave as a row vector. Okay, so when you need a vector, I would say either use this or this, okay, but not a rank one array like this one. Okay, never use this one when you want to perform neural networks or when you want to use vectors. Okay, and one more thing that you can do if you're not entirely sure what is the dimensions of one of your vectors, then you should throw an assertion statement like this. Okay, and to make sure in this case that a 5 by 1 vector is a column vector. Okay, these assertions are really not expensive computation to execute, and they also help to serve a documentation for your code. So don't really hesitate to use to throw in assertion statements like this one over here, and whenever you feel really like it, as it doesn't really reduce anything for your code. It actually more likely enhances the readability and making sure that you're in the right track when you're coding. And then finally, if for some reason you end up with a rank one array, then you can really reshape this as a equals a dot reshape. Okay, so if you end up as uh, a rank one array, I do suggest always printing after every matrix you do, just to double check. And in case you do that, no problem, you can always reshape it like the one that you're seeing over here. Okay, and uh, then we can say it's a 5 by 1 or a 1 by 5. You can change this to a 1 by 5 array as well. So it behaves more consistently, either a column vector or a row vector. Okay, so sometimes you would be very deep into your work, and it would be extremely hard for you to track your code because those intuitive effects of the rank one arrays are common to happen to really anyone. Okay, and can really mess up your code without knowing. And by eliminating the rank one arrays in your code, it could be much simpler, and actually it would be even cleaner to understand. So the takeaway are to simplify your code and don't use the rank one array, and always use either n by 1 matrix n by 1 matrices, basically column vectors, or a 1 by n matrices, or basically row vectors. Also, I encourage to test out some assertion statements to just double check that the dimensions of the matrix and the arrays are also aligning with your goals. So don't really be shy by calling those reshape operations to make sure your matrices are or your vectors are the dimensions that you want it to be. And finally, I just hope that this set of suggestions would help you to eliminate the cause of some bugs from your Python code that you're literally writing right code, but this simple thing would kind of ruin all of your computations actually, and you would not know why it's behaving that way. Okay? And it would really make coding easier and simpler for you. And this is it for so far. And yeah, I hope this was beneficial, and I'll see you next week. Thank you.